Yes, some of you may have seen a tweet that said that this talk is going to be about security in blockchains. It's not. But so I'm going to stick to the abstract, which was building a blockchain in Erlang. It's going to be partly about blockchains in general, and then more specifically the Aeternity blockchain system that I'm working on, and then how we have specifically solved some problems. I have given some talks before about why one would choose Erlang to begin with, so you can find those on YouTube from Codebeam Stockholm and also from some Erlang workshop before. So I'm happy I won't have to give that a third time. So basically, any talk about anything in blockchain has to start by explaining blockchain technology, or are you all hardcore blockchain experts? This is a beginner talk, so I don't think, oh, okay. It's still going to be a very brief introduction. So the blockchain, you can see that essentially as a very write-expensive append-only file system. So it starts with block 0, which is called the Genesis block. It mainly contains, certainly in our system, governance parameters, which are basically system-wide parameters for the blockchain. And then you create blocks that are identified by a hash. Essentially, you pack a bunch of transactions into the block, and that's the interesting stuff. That's the actual work. And then you have some headers and a state tree. I'll talk a little bit more about that afterwards. And then you hash everything together, and then you get the top hash, and you include in the hash set the previous hash of the hash of the previous block. So that way you can know exactly where that block is in the chain. This also makes it a read-only. Once you've added that block, it's going to be immutable, because if you would change the previous pointer, it would change the hash, and then it would no longer be a valid block. So essentially, this is where you make sure that this is a valid block that can be attached to the top of the chain, and then you keep adding blocks on top of that. So that's sort of the blockchain. Now, there are essentially two major blockchain systems. One is Bitcoin, which is, of course, very famous because everyone who wants to make high-risk investments is following the Bitcoin rate, which I am not because I lost the key to my Bitcoin wallet. And then there is Ethereum. So Ethereum is a more general blockchain which specializes in smart contracts. So essentially you store programs in Ethereum, and then you can execute those. And then you have to pay a gas cost in order to execute them. So the thing about Ethereum then is that, well, to an extent also Bitcoin, but since Ethereum handles a lot more state, they added something they call a state tree. So for each block, you have the top hash of a tree that has all the relevant state for the transactions that were executed in that block. So actually in Bitcoin, for example, the original way, if you wanted to make a transfer of funds from one account to another and you wanted to figure out the balances, you essentially had to go back and look at previous transfers and calculate the balance. But if you have a state tree, you look up the balance in that tree. So that is sort of the relevant state for those things touched by those transactions in that block. So it makes it a lot cheaper to know the state of the blockchain, which is a good thing because these can get fairly big. A key point with blockchain technology is that they are no-trust systems. They're distributed systems, but you don't trust anyone. This makes it almost impossible to use any regular techniques for speeding up the consistency or the consensus protocols, because just about every distributed algorithm you know relies on you trusting the other nodes. So you have to think differently when you work with blockchains. And essentially the meat is in the cryptographic proofs and the algorithms, basically the hashing and proving. I will get into the proof of work a little bit later. So that's one thing, being able to verify that this is the right block and it hasn't been modified, so that data becomes immutable and you know that they are in the right order and everything by design, mathematically. The other thing is you want to work with incentives. You want to make it profitable to cooperate, make it profitable to do the right thing, and expensive to do the wrong thing. So there are attacks, for example, that there are known ways where you can break any blockchain. You just have to make it so expensive to do it that no one would want to try. So, yeah, I talked about the state tree. So, since it was mentioned that this was going to be about security, I threw in a security slide as well. So, this also becomes sort of a consequence of the no trust aspect. That, well, you can proof your own node, but that's basic node security. You use firewalls, you configure your web servers properly, you write your code so that it's fault tolerant. So I don't think there is that much to talk about in specifically about how we approach security. We do the things you would normally do if you write a software system in just about any language. So Eternity is, well, it's been around for about, I think, 2.5 years. So we're approaching our mainnet launch. It's actually scheduled for the last week of November. And the goal is to provide an open source platform, free for everyone. The code is available in the Aeternity GitHub. You can actually even go in and peek into our project management, the pivotal tracker that we're using. It's open, at least for reading, for everyone. So it's a very open project. And Eternity is running, for example, an incubator in Liechtenstein, sponsoring some startups. And we're actively seeking cooperation with universities, researchers, and also startups. Anyone who has an idea for how to build the next great application on blockchain. We're also hiring and definitely looking for new early adopters. So the thing that's a little bit different with the Eternity blockchain is that we've been trying to take the best ideas, sort of the more or less proven ideas in the blockchain space, and build them in as first-class objects as part of the core architecture. And this is essentially, nowadays, a lot of the research and these ideas and many of the alternative blockchain systems are essentially derivatives of either Bitcoin or Ethereum. And a lot of the features, I'm going to mention them briefly here, are built on top of, for example, mainly Ethereum, as smart contracts on top of Ethereum. So we're trying to make them into first-class objects. So the trivial one is spend transactions, obviously, so that you can transfer coin to some other account. And then you have the smart contracts, which are executable programs. And then there is something called state channels. Since the blockchain is expensive to access, well, it's not expensive to read, but it's expensive to write to the blockchain. You don't really have, you're not able to run a lot of transactions per second in any blockchain system. In Bitcoin, it's 4 to 6 transactions per second, I think, in the entire Bitcoin system. Eternity has slightly better performance. It's about 20. In our current load tests, we're running 30 to 40. Our design should have at least a theoretical capacity of 100. I don't know how close we're going to get to that. There are much faster blockchain systems. They usually use a different consensus mechanism that in some way sort of introduces trust, like proof of stake, where you essentially identify some actors as trusted, and then you can do things faster, like you normally do. If you have trusted actors, you can achieve speed in the normal with the normal techniques. So state channels is a way to sort of take funds out of your account, put them into a sort of a logical channel that you set up with another party, and then you can very quickly transfer funds or execute contracts, and you don't have to pay anything because you're not on the chain. And then you can either snapshot to the chain periodically, or when you close the channel, you update the balances, and then you have to pay a fee for doing that. But that means that you can get up to more than 100 transactions or a few hundred transactions per second in your dialogue with the other. So then you can actually do real-time interaction. Oracles is a way to access outside data. So you could have a web service, for example, and you post an oracle, which is essentially an object that describes what kind of queries you serve and the format of your replies. And then people can call on your oracle and ask for an update, and you deliver the update, and then they pay when they send a query, and you pay hopefully less when you deliver the response. So then you can make money by responding to queries from the outside world. And that could be stock market prices, weather reports, whatever. Hopefully you think of something else beyond that. And then we have a naming system, so far experimental. That's instead of just having to deal with the hashes, account hashes and hashed identifiers of contracts, you can actually name them like in the DNS system, which makes it easier. And the thing about these things being first-class objects is that when you can actually write smart contracts where the contract language and the libraries actually know about all these things and can deal with them inside the contract. So it makes it a little bit cleaner. It also allows us to do things a little bit faster and easier for the users. So the consensus, this is sort of the heart of any blockchain system, we use something called Bitcoin NG, and it's not actually Bitcoin, but it kind of builds on the traditional Bitcoin consensus, where you do mining. Mining is the sort of the work you have to put in order to be able to post a block on the chain. Essentially, you collect transactions, you create a candidate block, and then you have a field called a nonce, and you have to tweak that nonce and try to solve a puzzle. And that puzzle can be slightly different in the traditional Bitcoin world. You tweak that nonce, and then you try to get the resulting hash to fall into a certain window. So that counter is the only thing you can change. Everything else is static. And then you keep updating that and hope that you hit that hash window. And then increasing the difficulty means shrinking that hash window. Then it becomes more expensive to create a block. And of course, if you're trying to do this, just hashing until you find the right hash range, then you understand why Bitcoin uses up so much electricity, because this is compute intensive. So anyway, this is also why, partly why it's hard to get really good performance. You actually deliberately want to slow this down so that a bad actor can't just add a lot of fake blocks on the chain. So the thing about Bitcoin NG is that once you successfully created a new block on the chain, you can keep creating microblocks after that, every other second, packing more transactions. You get paid a little less, but you get paid for all those blocks, and you're actually then actively adding transactions to the chain until a new key block, real block, comes along, until the next miner solves the puzzle. And then it becomes a leader election thing. The miner who solves the puzzle becomes the leader and gets to generate microblocks until the next puzzle is solved. And the puzzle that's solved, that's called proof of work. And instead of that hashing problem, we're using something called cuckoo cycle. And essentially what that does is that it generates a random tree, a bunch of random nodes, and with connections, and then you're supposed to find a cycle of exactly length 42 in that random tree. And it's not, essentially you just have to visit all the nodes and all the connections, and you have to update counters so that you know which paths you visited and everything. It's a fairly trivial problem, but it's memory latency hard, because you're making millions and millions of memory accesses. This, we think, is a good thing, because the problem with a compute-intensive or hash-intensive proof of work is that if someone builds a very advanced ASIC, they can gain an advantage in mining power. And you don't want that, because then you get a centralized mining network. Ideally, you would want all the users to be able to mine and make money mining. Nowadays, it's almost impossible, or it's hard to make money mining as a sole user in Bitcoin. Because using a GPU, for example, is not cost effective. You're spending more money on electricity than you're actually gaining in miner fees. So the cuckoo cycle is supposed to be, hopefully, then a simple and more democratic mining algorithm. It seems like it's going to actually be it's nowadays ASIC friendly because you can pack so much memory on an ASIC today that you can still make an ASIC that outmines any CPU. So what we thought that we'd try to do is to sponsor development of an open source ASIC design that's very cheap and low cost that anyone can buy, and then sort of defeat that mining advantage that way. So then if it's going to be ASIC friendly, then make it as ASIC friendly as possible so that you can make a really cheap ASIC, and then you can still be democratic. So, and then we use some encrypted communication protocol called noise. For those who don't like TLS, perhaps, it's easier. It's a lot simpler than TLS. And you can use it if you want to. So this is sort of an illustration of the Bitcoin NG, that you have these key blocks, and whoever gets the key block can then punch out microblocks every 2 seconds. And this is how we can get up to some 100 transactions per second. There are challenges. One challenge is to be able to fill the microblocks completely. So you have to be able to sort of get all those transactions and peel them off the transaction called the mempool, or the transaction pool, and fill the blocks optimally in order to get to the maximum transaction throughput. But an advantage here also is that you get confirmation, at least some confirmation, very quickly. If you pay for a coffee in Bitcoin, it can take half an hour before you get confirmation. And of course, the coffee vendor is not going to force you to stand there for half an hour before he gives you the coffee. So then you agree to a zero confirmation payment. Essentially, you don't even check whether you actually got the coin. So here you can check because it's going to come within seconds at least. It's going to be a weak confirmation. I'm not going to get into that, but at least it's going to be much better than zero confirmation. So the thing about, since we're making these different features into first-class objects, what we're doing is essentially we create a transaction-oriented API. Maybe I can go to that slide first. These are our transaction types that we support. So you could say it's a data-driven API. So you have the Oracle register, Oracle extend, Oracle query, Oracle response, name preclaim, name claim, name transfer, name update, name revoke, and then you have channel transactions, create a channel, deposit tokens into a channel, withdraw tokens, force progress has to do with making sure that a contract is actually completed before you close the channel, and then a bunch of different ways of checkpointing the channel and closing in different ways and handling disputes. So, and this is a bit different. If you compare to Bitcoin, Bitcoin has only spend transactions and about 6 different types of spend transactions. Ethereum pretty much has one type of transaction, and that's, well, a simplified version is spend, but then it's about calling contracts. And then you have to do all the work in contracts on top of it, which is very flexible. But, so this is our approach. So then a core part of the system is we've created a behavior, which is sort of an Erlang design pattern, where you can plug in a transaction type, and it has a callback API, where most of the work is in check and process. So check is before committing and processes when you're actually doing the work once you commit the transaction, and update all the states and everything. And then you have some serialization callbacks so that there is an external format which is pretty much the same as Ethereum has. So in order to add a new transaction, then you write a module where you implement those callbacks. And then for the consensus algorithm, it basically just checks, verifies that a transaction is signed, verifies the signatures, and then processing the sort of unpacking the unsigned transaction and doing work on that. So for the smart contracts, we've actually implemented, or we are implementing, a bytecode evaluator inside Erlang, which is pretty much Ethereum compatible. So we're using the Ethereum bytecodes. We've tweaked a few bytecodes and added some of our own. So Ethereum has a contract language called Solidity. And they have a bunch of tools that we can't compete with, an IDE and simulators and debugging environments that are, we don't do any of that. But for Erlangers, that will feel comfortable. You have your Emacs, you have your shell, that's all you need, right? We are also developing our own contract language called Sophia, because the first meeting was in Sofia, Bulgaria, where we nailed down the syntax. And it's fairly similar to OCaml. So it's an ML-like functional contract language, but it does compile down to pretty much the same bytecode. And one thing about contract evaluation is that you want to use contracts also in state channels, so then you have to be able to run off-chain and on-chain. But of course, when you're testing, you also want to be able to run off-chain. And since it's implemented in a functional language, off-chain is, basically the environment is just the data structure that you create, so it's not really a big problem. This is actually where it becomes very simple to, this kind of thing is very easy to do in a functional language. Now, one concern is that the bytecode evaluator written in Erlang should be very slow. It's possible that I doubt that it would be faster than the Ethereum VM, but so far it seems to be okay. We haven't done really serious benchmarking, but usually contracts are very short. And so I don't think performance is going to be a big problem. We're going mainly for correctness right now anyway. So I talked a little bit about this, the state channels. And one of the big problems with state channels is you could say that this is a limited trust environment. When you if the blockchain is a no-trust environment, everything is validated, and this is why it's so expensive. The idea of the state channel is that you're off-channel, but you're still working in sort of a limited trust. What we do is that we require the parties in the channel to co-sign everything. I think I had a picture that kind of illustrates this, where, for example, I want to transfer some coin to the other party in the channel. Okay, so I should explain one thing here. what we decided to do is that inside the Erlang node, we're running the state machine for the state channel. But the client is probably sitting as a WebSocket client running in JavaScript or something. But we don't want them to have to implement the full state machine because that's going to be complicated. It can get fairly complicated. And Erlang is really good with building state machines. So we're building the state machine inside Erlang, and then the client sits on the side. So then the interaction becomes the client sends a transaction request saying, I want to transfer coin to the other party. And then the Erlang state machine sends a signing request back and say, okay, here is a transaction object, sign it please, because you don't want to install the keys in the node. It would have to have your private key in order to sign it, and that would be a bad idea. So the client has the private key, so then you have to create the object, send it back, and saying this is what you need to sign, and then it sends a message back. But then you end up with these transition states that can be fairly significant in time. So once this is signed, you send an update request to the other party, and then that FSM sends a signing request to its client, and it signs it back, basically approving the operation. And then it's in a wait state here. But if while we are here, for example, the other client has decided to initiate an update, then you get a conflict here. So you get you complicate the state machine quite a lot when you do this. But the interface here becomes reasonably easy. We even have a command line interface that implements this. So it's easy enough you send a command and then you get the signing request back. So this is where it really pays off to do it in Erlang. And also, this is an area where these are the processes, as far as I could remember, that are involved in a state channel. So you would have a WebSocket handler. You spawn a process that sits on that takes care of the WebSocket communication. It spawns a state machine, channel state machine, which creates a create transaction and sends it to the chain, which is not in this picture. And then, to be sure that the transaction is actually on the chain, you usually want to wait for a number of blocks to pile on top of that block that has your transaction. So then you spawn a chain watcher that waits for confirmation for how many blocks you want to have confirmed on top. It depends on how sure you want to be that the transaction is there. You could have a confirmation of 0, essentially, but normally you would wait maybe 3 blocks or something before you say, okay, now I know that this is secured on the chain. So then that's a chain watcher that sits there. And then you have the noise connection process that talks to a gen TCP process. So this is where the TCP communication is terminated. This is where the encryption and the noise state machine is. And this one does the encode decode for the channel FSM, and that does the channel state machine. And then we also have a state cache, so that if you would happen to disconnect, the node actually keeps your entire state so that you can then reconnect and be back at the exact same place that you left, where you left off. And of course, that process, which is a different shade because it's permanent, so it's the same process for all the channels, but it will detect if that process dies, and then it will start a chain watcher, which essentially waits for it to come back up. Let's see. No, it waits for it to be confirmed as closed. And then once that's done, it will move the state to persistent storage. Okay. So this is also an area where it becomes very convenient to use Erlang. So, and one of the things about this is that so how many of you are Erlang programmers? Pretty much everyone. So then I don't have to explain really but one of the things I found when you write these types of FSMs is that if you really separate the concerns, you get several simpler state machines. So then each state machine is reasonably simple. You just have to think about what happens in the failure cases and interaction cases. But it makes the problem a lot more manageable. Okay, is this too small for you to see? We're using gproc pubsub. So if you're all Erlang programmers, you actually know what gproc is, right? So by some weird accident, there are actually a few of my components that are running in Eternity. That's what you get for hiring me, I guess. So, for example, here, the conductor, which is the one that takes new block candidates and puts them on the chain or gets blocks from the network, when it sees a new block, it publishes an event saying the top of the chain has changed. So for example, the minimum depth watcher subscribes to that event. So when it gets that, it checks whether its condition is now met, that enough blocks have piled on top. So once it finds that that's the case, it has a callback module, and it calls the appropriate callback saying, now you can continue, now you have the confirmation you needed. So, another big thing, and this is actually, I noticed that Ethereum has had some problems that they call the DOS, denial of service problem. It's not really a denial of service problem, it's just that the system gets overloaded. And so of course that happens also when we run our load tests. There are a lot of expensive processes, and so the risk is that you get so many transactions flowing into the system, for example, that you can't manage them. And for example, the mempool, where transactions wait to be included in a block, can grow up to, say, if it's tens of thousands of transactions waiting there, you can possibly run into problems. So the idea with jobs is you put queues, especially on the outskirts of your system, and you identify the places where work can enter the system. For example, the WebSocket API, the HTTP API, and Gossip is one. That's where you broadcast your transactions. And Sync is where you sync up with other nodes, and also you broadcast blocks through the Gossip. And of course, there are different parameters here. Some work, for example, new requests here, you may want to reject them before you start rejecting Gossip traffic, because this is stuff that the system has already invested work in. And also the mempool is kind of in the middle. We have a queue on that too, which kind of violates my rule that you normally don't want to have load regulation in the core of the system if you can avoid it. But on the other hand, we have a sampler on that. So basically, if the size of the mempool starts growing, then we try to push back into the, so that we start rejecting work and start queuing it so that we can stay at reasonably good throughput. And because you need to be able to tweak that in a realistic test environment, like you spin up a test network and then you run up, you start your load generators and then you try to kill the system with overload. So what we've done is that we have a JSON schema, so you can actually parameterize the system using YAML or JSON config files. And then every queue is, you have the parameters and they have defaults in the schema, and then you can tweak those, and then you can restart nodes and you can rerun your tests. So that, because essentially you have no idea what those parameters are going to be before you've load tested it and profiled. So, yeah, mainnet release, end of this month. We have a huge backlog. We're going to continue developing stuff. We've been trying to get all the sort of the basically usable features in and robust functionality so that you can actually start doing real work on it. And there is a testnet that has been up and running for about 6 months or so, I think. But that one we just keep, when we have a new release every other week, we just throw away the old stuff and start with a new database. So you can't use it for any serious stuff. But if you want to run some prototyping, you want to test stuff, we have a forum where you can ask questions or just contact us and we'll see if we can help you a little bit more actively, because we're eager to get users and we're sort of now coming into the phase where that's going to be the top priority. So, do you have any questions?
Hi there. Sounds like a really interesting project, but I just wonder if you could go into a bit more detail about what you were looking for when you were thinking about the contract language, and in particular how important is kind of an exact maths model rather than a floating point or integer maths model.
The contract, why we decided to design our own contract language, you mean?
Yeah.
Yeah, so yeah, we're partial to functional programming in general, but one thing is that apart from creating cleaner code, more readable code, because that's a fairly important factor. These are sort of shared programs that other users are supposed to, I mean, essentially you want to read them and verify that they're correct. And the clearer the code, the easier it's going to be for others to trust it. But also, it's going to make it easier to run proof checkers so that you can actually develop tools that can make a better analysis of how much your contract is going to cost, for example, and verify that it actually does what you expect it to do. And we think in this environment that's a pretty good thing. Normally, otherwise you have to have your fake test net where you test your contract manually. But we think it's a good investment. We actually have some other languages on the way that are more like Bitcoin's scripting languages, that for very simple things, you don't really want to fire up the entire or the full featured code evaluator. You can make it go much faster if you have a sort of a more dedicated scripting language for certain things. But that's not ready yet. Did that answer your question? I didn't hear that.
Do you use floating point maths or discrete decimal?
We don't do floating point, no. I don't think Ethereum does either.
Okay. Well, I don't think we have time for any more questions right now, so catch Ulf later if you want to talk to him.
Okay. Thank you.